So next we are going to see what are the steps required for transmitting a character from ARM to PC. So let us take you are going to transmit a character A from your LPC2148 microcontroller to the PC. What are the steps required for that? These are the steps. One by one we will see. This is the first step. So first step is that set P0.0 pin as transmit pin, that is TXD pin, and P0.1 pin as receive pin of UART 0. Configure P0.0 as transmit and P0.1 as receive of UART 0. Right? So I told that whatever peripheral you are going to configure, the first and foremost step is that you need to configure the functionality of that particular pin as your required pin. So by default P0.0 and P0.1 will be GPIO pins, but now you are going to configure a peripheral known as UART. So you need to configure the functionality of P0.0 and P0.1 as UART TX and RX. How will you do that? For that, since you are going to configure the functionality of P0 port 0 pins, you are going to use pin cell 0 register. For configuring port 0 pins, you are having pin cell 0 and pin cell 1. But now we are using only pin cell 0. Why? Pin cell 0 is used for configuring functionality of pins from P0.0 to P0.15. So since you are configuring the functionality of P0.0 to P0.15, if you want to configure the functionality of these pins, you should use pin cell 0. If you want to configure functionalities of P0.16 to 31, you should use pin cell 1. But now we are configuring only P0.0 and P0.1, so we are using pin cell 0. So this is a pin cell 0 register. Here you are going to configure P0.0 and P0.1 as TX pin and RX pin. By default, these two pins will be GPIO pins. So how will you configure P0.0 as TXD pin? You need to write a value known as 0, 1 to bit number 1 and 0 of pin cell 0 register. So if you are writing 0, 1 to bit number 1 and bit number 0, that is bit number 1 will be 0, bit number 0 will be 1. So if you are writing 0, 1 to bit number 1 and 0 of pin cell 0 register, you are configuring P0.0 as TXD pin of UART 0. Similarly, you need to configure P0.1 as RXD pin of UART 0. How will you do that? You need to write 0, 1. So same 0, 1 you should write to bit number 3 and 2. If you are writing bit number 0, 1 to bit number 1 and 0, you are configuring P0.0 as TX pin. But if you are writing 0, 1 to the next 2 bits, that is bit number 3 and bit number 2. So bit number 3 will be 0, bit number 2 will be 1. So if you are writing 0, 1 in bit number 3 and 2, you are configuring P0.1 as RXD pin. So by writing 0, 1 to bit number 1, 0 and 0, 1 to bit number 3 and 2, you can configure P0.0 and P0.1 as TXD and RXD. Right? So these 4 bits, the first 2 bits you need to write it with 0, 1. Again the next 2 bits also you need to write 0, 1. So if you are writing pin cell 0 register as a whole, what value you should write? 0, 1, 0, 1. So what will be the hexadecimal equivalent? It is 5. Right? Last 4 bits will be 0, 1, 0, 1. 0, 1, 0, 1 means it is 5. All the other bits you are keeping it as it is 0, 0, 0. So pin cell 0 equal to 0x 0005 means you are configuring P0.0, P0.1 as UART 0, TX and RX. Similarly, if you want to configure UART1 pin as TX and RX, you need to configure P0.8 and P0.9. Right? The value remains the same. 0, 1 if you are writing to bit number 17 and 16, you are configuring P0.8 as transmit pin of UART1. Similarly, if you are writing 0, 1 to bit number 19 and 18, here it was 17 and 16, then here it is 19 and 18. If you are writing 0, 1 to bit number 19 and 18, you are configuring P0.9 as TXD pin of UART1. So these 4 bits are used for configuring UART1. These 4 bits are used for configuring UART0. Right? But the value remains the same. So if you are writing this 5 here, this represent bit number 16, 17, 18, 19, and if you are writing 5 at the end, this represents the bit number 0 to 3. So if you are writing 0005, you are configuring UART 0. If you are writing 005, 0000, you are configuring UART 1. In step number 2, we are going to configure parameters for serial communication. So what are the parameters for serial communication? These are the parameters. So first parameter is the data length. How many bits you are going to transmit or receive at a particular time. That is known as a data length. Generally the data length will be 8 bits. Right? You will be transmitting 8 bit of data in a particular data frame. Each data frame will be having 8 bits. In some of the microcontrollers you can have 9-bit data transmission also, but by default the data transmission length will be 8 bits. Then next parameter is whether you are going to have a parity bit or not. So parity bit is used for error correction, right? You are having two type of parity. It is known as odd parity and even parity, right? So let us take you are having a 4-bit number, say 1110. So how will you find out the parity of this number? You need to count the number of ones in that number. So here you are having 3 ones. So the number of ones is odd. So you are telling that it is having odd parity. And in this number you are having 0101. So here how many ones are there? 2 ones are there. So since the number of ones is 2, we are telling that it is having even parity. So this is known as odd parity and even parity. So if you are adding an parity bit for serial transmission, you can identify whether your number is having an odd parity or even parity. So for representing odd parity, you will make this parity bit as 1. For representing even parity, you will make this parity bit as 0. So if the parity bit is 1, that means your number is having odd parity, and if the parity bit is 0, it tells that your number is having even parity. So that is the use of parity bit. And there is another bit for enabling or disabling this parity also, right? So in this controller you are having a separate bit known as parity enable bit. So if the parity enable bit is 1, then only you should take care of the parity bits, right? So if the parity enable bit is 0, that means the parity will not be there, so no need of considering the parity bit. Otherwise you need to consider the parity bit. So the second parameter is parity bit. The third parameter is stop bits. So for a data in a particular data frame, you will be having start bit, data bits and stop bit, that we will see in the next slide. So how many stop bit you are going to use for your current serial transmission, that should be configured here. So generally you can have one stop bit or two stop bit. If you are having two stop bit, some more error correction will be incorporated. So you can configure either one stop bit or two stop bit. And the last configuration you need to do is the baud rate. Baud rate means how many number of bits you are going to transmit or receive per second. So this decides the speed at which you are performing the serial transmission, right? And the unit will be bits per second, right? So by default the baud rate will be 9600 bits per second. That means by default if you are transmitting or receiving, the number of bits per second will be, or the baud rate will be 9600 bits per second. So these are the 4 parameters you need to configure in the case of serial communication, right? So this is a data frame format which I have told just now. So this is how you are transmitting a character through serial communication. This is known as a data frame format. How each bits are sent or received in the case of serial communication, right? So by default, you can see that now you are going to transmit a data. So for transmission, you will be using TX line, right? So by default, both the TX and RX line of LPC2148 will be pulled up to VCC. In the case of LPC2148, you are having 3.3 volt VCC. So by default, if no transmission and reception is there, both the lines TX and RX line will be pulled up to VCC, right? So if no transmission or reception is there, if there is not any transmission or reception, both the pins will be in VCC, right? And for time being, let us take you are going to transmit a data such as 1001, 1011. If you are going to transmit this data, what will happen? Whenever you are initiating the transmission, the TX line will be pulled down from VCC to 0. So when the receiver is identifying that that pin is changing its voltage level from 0 to 1 to 0, right? So whenever there is a falling edge or whenever there is a transmission from 1 to 0, the receiver will identify that some data is coming. So this bit, the first 0 bit is known as a start bit. So by default, both TX and RX will be in pulled up state or pulled up level. It will be in VCC level. When the transmitter is going to transmit a data, it will suddenly make the logic 1 signal to logic 0 in the transmission line. So that transmission line is connected to the receiver of RX line of receiver. So when the receiver is identifying that there is a 0 coming in the coming in that line, it identifies that it is a start bit. So start bit is nothing but 0. After that, 8 data bits will be coming. So in my case, the data bits is 1001, 1011. So correspondingly in one cycle, first bit will be sent, then 0 bit will be sent, like that 8 data bits will be sent. So first bit which you are sending will be LSB, the last bit which you are sending will be the MSB. The data will be sent like this. After sending all the 8 data bits, next you will be sending stop bit, right? So stop bit is nothing but a logic 1 signal or 1 signal, because start bit will be 0 bit or logic 0 or 0 logic 0. Stop bit will be opposite of the start bit, that is 1, right? So by using, what is the advantage of using stop bit? By using stop bit, you are taking back the voltage level from the previous state to logic high state, because I told whenever there is no transmission or reception, the logic level will be in logic 1. So similarly, after the completion of 8 data bits, the stop bit will take back the TX or RX pin to logic 1, right? So stop bit will be logic 1 or 1 will be the stop bit, 0 will be start bit. So this whole thing is known as the data frame for a serial communication. So the data frame consists of a start bit, 8 data bits and a stop bit, right? And what will be the time taken for transmitting each bit? That is based on the baud rate. Baud rate means number of bits transmitted or received per second. By default, the baud rate is 9600 bits per second. So what will be the time taken for one bit? 1 by 9600. So 1 by 9600 will be the time taken for sending each bit, including start bit and stop bit. So total you will be having 10 bits in a particular data frame format. One will be start bit, 8 data bits and 1 stop bit, total 10 bits. If you are having 2 stop bits, I told you can have 1 stop bit or 2 stop bit. If you are having 2 stop bit in a particular data frame, you will be having 11 data bits. Otherwise, by default, you will be having only 10 data bits in a particular data frame format. So in step number 2, you are configuring these parameters. What are the parameters? The data length, parity bit, stop bit, and in the next step we will be configuring the baud rate. So here in step number 2, you are configuring the data length, whether you are having a parity or stop bit. So how will you configure that? So for configuring the parameters, you are using a register known as U0LCR, UART0 line control register. Right? If you are configuring UART1, you should take UART1 line control register or U1 line control register. Here I am using UART0, so you are using UART0 line control register. So in this register, again how many bit register it is? I told it is a 32-bit microcontroller, so all the registers will be of size 32 bits. Right, but you will not be configuring all the 32 bits. Based on our application or based on our functionality, we will be configuring only certain bits, right? So here you are going to configure certain bits. So bit number 1 and bit number 0 is used for configuring the word length. Word length means the data length for serial transmission, right? And by default, the data length will be reset to 00. That means by default, data length will be 5 bits. But I told generally in the case of a serial transmission, you will be using 8-bit data transmission. So I am in this case, I am going to configure 8-bit data transmission, right? So how will you configure 8-bit data transmission? You should write 1 1 to bit number 1 and bit number 0. By default, it will be 5 bit. You can see these are the reset value. Reset value means by default, these two bits will be having a reset value 0. So 00 means 5 bit transmission, 5 bit data length. But generally you are using 8 bit. So I am going to configure 8 bit data length. So what value you should write? You should write 1 1 in bit number 1 and bit number 0. So 1 1 in bit number 1 and bit number 0. Right? You are writing 1 1. Next bit, it is used for configuring the stop bit, and here I am going to configure one stop bit. So what value should write? Bit number 2 should be written with a value 0. So here bit number 2 I am writing a 0. So I am configuring one bit stop bit. Then the next bit is parity enable. For time being, you are going to disable the parity. I am not using a parity. So this parity enable bit will be 0. So which is that bit? Third bit. Third bit you make it as 0. So you are disabling the parity. Disable this for disabling the parity, you are making third bit as 0. Third bit as 0. Then the next two bits 5 and 4 are the parity select bits, but since in bit number 3 you have disabled the parity, you no need of considering these two bits because parity is already disabled. So for time being, you are making bit number 4 and 5 as 0 0 itself. Bit number 4 and 5 as 0 0, right? Whatever value you are writing here, it doesn't matter. For time being, you are writing 0 0. Why? Because parity is already disabled. Then brake control also I am writing it as 0. Now I am not using a brake control, right? What is meant by brake control we will see in some other lecture. So in this case I am using or disabling the brake control, making it as 0. And the last bit, that is 7th bit, you need to configure. You are configuring 8 bits. Actually U0LCR is having 32 bits, but you are configuring only 8 bits. So the 7th bit, bit number 0 to 7, so the 7th bit is known as divisor latch access bit. So this bit alone we will see in the next slide what is the importance of this bit. All the other bits I have configured now. So what value for time being you can write it as 1. You are enabling access to divisor latches. What is meant by this divisor latches and why you are enabling divisor latches? I will explain in the forthcoming slide. Now you assume that this divisor latches is 1, or I am enabling the divisor latches. So if you want to make all this configuration, that is 8 data bits, 1 stop bit, disable parity, break control I am disabling, and divisor latch access bit as 1, enabling divisor latch access bit. What value should be returned to U0 LCR? Right? 8 data length means you should write 1 1, so 1 1. Stop bit I am having only one stop bit, so 0. Parity enable I am disabling parity. Then the next two parity select bit also 0 0. Then break control it is 0. Last divisor latch access bit I am enabling. So what is this value? It is 0x83. So if U0 LCR you are writing with 0x83, what does it mean? You are configuring word length as 8, stop bit as 1 stop bit, and you are disabling parity. Parity select is not there. You are disabling break control and you are enabling divisor latch access bit. Right. So U0 LCR equals 0x083 means you are configuring all these parameters required for serial transmission. In the next step, you are going to configure the baud rate. Baud rate is one of the important parameter, right? So in this step, you are going to configure the baud rate as 9600 bits per second, right? So here you should keep something in mind. All your peripherals present in LPC2148, generally all the peripherals exceptions are there. So basic peripherals, all the peripherals are connected to a clock known as VPB clock or P clock, peripheral clock. You are having two types of clocks, C clock and P clock. C clock stands for core clock, right? But all your peripherals are connected to a bus known as VPB bus, that is known as VLSI peripheral bus. All these things I have explained when I was explaining the architecture of LPC2148. You can go through that. I'll give the link of that video in the I button here, right? So there you can see all the peripherals are connected to VPB bus or VLSI peripheral bus. So the clock supplied in the VLSI peripheral bus is known as P clock, right? And while you are configuring the P clock, I have configured it as 15 megahertz. That also I have explained. So by default, your P clock will be 15 megahertz. That is your core clock divided by 4. So here I have configured the core clock as 60 megahertz. So by default, the core clock will be configured in 60 megahertz, and I am using a crystal oscillator of 12 megahertz. So from the 12 megahertz crystal oscillator, you are multiplying the 12 you are multiplying the crystal frequency by 5, and you are getting C clock as 60 megahertz, right? And from that C clock you are having a division by 4. So you are dividing C clock by 4 in order to get the P clock. So your actual P clock you are, what you have configured is 15 megahertz. So by default C clock will be 60 megahertz if you are using 12 megahertz crystal, and P clock will be 15 megahertz. That means you are dividing C clock by 4. So whatever calculation you are doing with the peripherals, you should take the clock as P clock, because all your peripherals are connected to VPB bus, and in VPB bus you are using P clock. Don't take C clock for the calculation, right? So here your P clock or peripheral clock is operating on 15 megahertz. So for the calculation of baud rate, that is 9600 bps, you need to use 15 megahertz as a clock input, right? So next step, in this step we are going to see how to configure this baud rate with 9600 bps, right? So for configuring the baud rate, you are having two registers known as U0DLL and U0DLM. U0DLL means U0 UART 0 divisor latch LSB bit. Similar divisor latch LSB register. Similarly, you are having one more register known as U0DLM, divisor latch MSB. So these are the two registers, U0DLL, U0DLM. By configuring these two registers, you can configure the baud rate of UART. Right? My aim is to configure the UART with 9600 baud rates. So for configuring that baud rate, you need to configure these two registers, DLM and DLL. So what if you are writing a particular value into these two registers, corresponding baud rate will be generated. So if you are writing a particular value, and you need to see that both these registers you are configuring only 8 bits. You are configuring only 8 bits of these two registers. So 16 bits you are configuring for configuring the baud rate. Right? So if you are writing a particular value in these two registers, corresponding baud rate will be generated. So here I need to configure baud rate as 9600. Right? So if you want to configure 9600 baud rate, what value should be written into these two registers? That is what you are going to see. So for calculating that value, you are having an equation, right, known as UART0 baud rate equal to P clock by 16 into U0 DLM plus U0 DLL into mulval by mulval plus divide val. Right? So this whole thing is known as baud rate generation or baud rate calculation equation. Right? And here who is generating this baud rate or baud clock? This baud clock is generated by a peripheral known as fractional baud rate generator. So fractional baud rate generator is generating the clock for this baud rate. My aim is to generate baud rate as 9600. So for generating baud rate as 9600, provided PCLK as 15 MHz, what should be the value of U0 DLL and U0 DLM and these? That is my aim. You need to calculate the value of all these things. This is not so important. This is only for the error correction. Your actual equation, your important equation is till here. If you want to have the error correction, you need to configure this also. Otherwise, that is not so important. Right? And here, one more thing you need to keep in mind. You need to configure the value of U0 DLL and U0 DLM. By default, U0 DLL will be having a value 1. You cannot make this U0 DLL as 0. Why? If you are making U0 DLL as 0, this whole term will be made as 0 and your baud rate will be having, it is something like something divided by 0. So divide by 0 error will be there. Your baud rate will be something like infinity. Right? So that cannot happen. So by default, U0 DLL value will be 1. So let us take one example. Let us take you are having PCLK as 30 MHz. You need to configure the baud rate as 9600 baud rate. Right? So you are starting with the U0 DLM value as 0. Right? Divide value as 0. Mul value as 1. So divide value 0, mul value as 1. So what will happen to this whole term? It will be 1. Mul value 1, div value 0. So this whole term for time being I am making it as 1. Right? Then U0 DLM is 0. Right? U0 DLM is 0. This is already 1. PCLK is 15 MHz. UART 0 baud rate is 9600. So you can calculate the value of U0 DLL. Right? You have made this term as 1, DLM as 0, PCLK as 15 MHz, UART 0 baud rate as 9600. So there is only one unknown term. So by substituting all this value, you will be getting U0 DLL value as 195.3125. If you are rounding off to the nearest integer, you will be getting as 195. Right? So if you want to generate 9600 baud rate, provided PCLK is 30 MHz, your U0 DLL should be 195. Right? Then what you are going to do is you are substituting this 195 back to this equation. Right? PCLK is 30 MHz DLM is 0, this term is 1, and U0 DLL I am substituting it with 195. So when you are substituting all this value, you will be getting back the baud rate as 9615.38. When you are substituting this 195 back in this equation with the other values, you will be getting the baud rate as 9615.38. Right? So your actual baud rate what you are going to set was 9600, but since you are substituting U0 DLL with 195, you are getting an error of 15.28. Right? So how our aim is to reduce this error to maximum possible value. So how will you reduce this error? For reducing the error, you are using this part of the equation. For reducing the error, you are using this part of the equation. So how will you reduce the error? You need to change the mul val and divide val. By default, you have taken mul value as 1, divide value as 0. You are going to change it. So in order to reduce the error, you need to change the value of mul val and divide val. And you need to keep this in mind. Mul val and divide val, the maximum value of these two parameters are 15. You cannot give a value above this, right? So in order to reduce the error, for time being I am making mul value as 15, divide value as 1, and I am substituting it back in the equation. So the baud rate I need is 9600, peak clock is 30 megahertz, DLM is 0, mul value is 15, divide value is 1. So it will be 15 by 16. So when you are substituting all this value, you will be getting U0 DLL as 183. Right? So by changing mul value as 15 and divide value as 1 and substituting this value in the equation along with the PCLK and DLM, you will be getting U0 DLL as 183. Previously you are getting U0 DLL as 195. Now you are getting 183. Then what you will do? Again you will substitute this back to this equation and calculate the baud rate. When you are substituting U0 DLL as 183, DLM as 30 megahertz, DLM as 0, PCLK as 30, mul value as 15, divide value as 1. By substituting all this value, you will be getting the baud rate as 906.53. If you are rounding off 906. So what is the error now? 5. So you have reduced the error from 15 to 5. How you have reduced? By changing the mul value and divide value. Right. So what is the final configuration now? PCLK 30 megahertz, U0 DLL 183, DLM 0, mul value 15, divide value 1. So when you are substituting all these values, what you are achieving, you can generate a baud rate of 9605. So by using the second part of the equation, you can reduce the error in the baud rate. So that is why it is known as fractional baud rate generator. If this part is not there, then it can be known as baud rate generator alone. So in the step number 3, what you are going to configure? You are going to configure the baud rate as 9600. So if you want to get the baud rate as 9600, value of PCLK should be 15 megahertz, U0 DLM should be 0, mul value 1, divide value 0, and by substituting all this value, you will be getting U0 DLL value. So what value should be written to U0 DLL in order to configure the baud rate as 9600? You will be getting it as 97, decimal 97. Right. So if you are moving decimal 97 to U0 DLL, you are configuring the baud rate of UART 0 as 9600. Why you are not setting all these bits? Because by default your PCLK is 15 megahertz. By default U0 DLM is 0, mul value is 1, divide value is 0. So that is why you are not touching on these values. You are configuring only U0 DLL, right? But sometimes you need to configure U0 DLM also. So here we are starting with PCLK 60 MHz, U0 DLM 0, divide value 0, mul value 1 and PCLK 60 MHz. So when you are substituting all these things, you will be getting the U0 DLL value as 390. 390, right? 390 cannot, it in decimal 390 means in hexadecimal 390 cannot be represented in 8-bit. I told in U0 DLL you can store only 8-bit, but if you want to represent 390 in decimal, you need to have 9 bits, right? But in U0 DLL you are having only 8 bits. So what you will do? Then you need to configure U0 DLM also in this case. So here I am making U0 DLM as 1, right? So by substituting U0 DLM 1 instead of U0 DLM 0, previously I have configured with U0 DLM as 0, but you are getting a 9-bit value. So I cannot configure 9-bit value in U0 DLL. So in order to change the 9-bit to 8-bit, you are making U0 DLM as 1. You will be getting U0 DLL as 135. So in this case, you need to configure U0 DLM and U0 DLL. Right. Again, error correction will be done, and finally you are getting U0 DLL as 110. So if you are having PCLK 60 MHz and if you want to configure the baud rate as 9600, you need to configure both these registers. U0 DLL as 110, U0 DLM as 1, right? So in this case, both registers you need to configure. But in our case, our peak clock is 15 MHz, so I don't need to configure U0 DLM. So U0, why I don't need to configure DLM? Because U0 DLL value is 97. That is coming in within the 8-bit. So that is why you are only configuring U0 DLL as 97. This is the third step. You are configuring U0 DLL as 97. You don't need to configure DLM because by default DLM will be 0. Right? So for configuring 9600 bits per second, provided peak clock is 15, you should configure U0 DLL register as 97 in decimal. I have told another bit known as divisor latch access bit. So what is the use of this divisor latch access bit? In this step I have told that you need to write a value 97 into DLL, right? So whenever you want to write a value into divisor latch access bits, in divisor latch bits such as U0 DLL or DLM, you need to enable these registers first, or you need to enable the access to these registers. You cannot directly write this value without enabling. So if you want to write value into DLL or DLM, you need to enable access to these registers. Why they have given like that? In order to have a protection. Because by mistake, if you are writing some value into DLL, your whole serial transmission will be affected. Right? By mistake, say for example, by mistake you are writing some value into DLL. What will happen? Your whole serial transmission will be affected. So in order to have protection over the baud rate generator or the serial transmission UART peripheral, there is another bit known as divisor latch access bit. It is known as DLAB. So if this DLAB bit is 1, then only you can write into these two registers. So before writing a value into DLL or DLM, you need to make the DLAB bit as 1. That is why it is given. When DLAB bit is 1, you can write something to this. Right. So that is done in the previous step. So that is a use of divisor latch access bit, DLAB. So if this DLAB bit or the 7th bit of U0 LCR is 1, that means you are enabling access to the divisor latches. What are the divisor latches? U0 DLL and U0 DLM. So whenever you need to write some value into these two registers, DLAB bit should be made as 1. Right? So that is a functionality of DLAB bit. So in step number 2, you need to make DLAB bit as 1, or you need to enable access to divisor latches. Then only you can write this 97 to U0DLM. So in step number 2, you should enable DLAB, and in the step number 3, you can configure divisor latches. Here I am configuring only U0DLL. And after configuring this value, what you should do, what will be the seventh step, what will be the fourth step? In the fourth step, you should disable the access to divisor latches. That means you are locking the access. Previously, you have enabled the access to divisor latches, then you are writing 97. After the write process is complete, you need to disable disable the access to divisor latches. How will you do that? You need to make this bit as 0. The remaining bits you need to keep as it is. Right? The word length, stop bit, parity enable, break control, etc. Whatever you have configured before, that should be as it is. Only the last bit, the seventh bit, you need to make it as 0. So when you are making this bit as 0, you are disabling the access to divisor latches. Right? So first you should enable the access to divisor latches, write the value to the divisor latches. That is why you are doing U0DLL equal to 97. That means 97 you are writing into divisor latches LSB DLL. So after writing that, you should disable it, or you should lock the access. Otherwise, again, if you are by mistake, if you are writing some other value, previous value will be overwritten and your serial communication will be affected. So once you have completed the writing to divisor latches, you need to lock it, or you need to, how will you lock it? By disabling the access to divisor latches. How will you do that? You need to make DLAB bit as 0. So in step number 4, you are making, you are disabling the access to divisor latches, and all the other bits will be the same. So what is the value here? 0 0 0 0 0 1 1. What is that value? U0 LCR equal to 0 3. Right? So in step number 4, you are writing U0 LCR equal to 0 3. That means you are making divisor latch access bit as 0. That means you are disabling access to the divisor latches. All the other bits remains the same. In step number 5, we will check whether UART0 is ready to send a new character. So for time being, we are skipping this step. We are going to the next step. We will discuss it little bit later. So in the sixth step, what we are doing, till step number 1 to 4, we have done initial configuration for the UART peripheral. After doing the initial configuration, what you should do, you need to transmit transmit the data through the UART peripheral. So what you should do, say in this example, you are going to transmit a character known as A, small letter A, through UART, right? So what you should do, whatever character you need to transmit through UART, you need to give that character into a register known as U0THR. U0THR means UART0 transmit holding register. So it is a register which is used for holding the data that has to be transmitted using UART. So after performing the initial configuration, whatever data you need to transmit, in my case I am going to transmit a character A, that A should be sent to a register known as U0THR. So what will happen? That character will be sent out through the TX pin of UART peripheral. Right. TX pin is P0.0 of UART peripheral. Right. But one more thing you need to keep in mind, before sending the data to the UART, you should check whether UART peripheral is ready to receive that character from the user. Right. Because sometimes the UART peripheral may be busy in sending the previous character that I have sent already to UART through this register. Right? Say for time being, you may have sent another character, say C, before sending my character, current character A, to the UART. So that transmission of character C may be in progress at the present moment of time. So before sending my current character A, you should check whether your UART is ready to receive the new character. If it is ready to receive, then only you should give this character to U0THR. Otherwise, your data will not be transmitted correctly. Right? So how will you check whether UART is ready to receive a new character? How can you identify? UART is having how does the UART converting your data serially? So let us take you are giving a character A. How it is getting converted to serial data? So ASCII corresponding ASCII value of a character whatever you are sending, that ASCII value will be taken by UART, right? And it will be sent to a transmit shift register present in UART. In UART peripheral, you will be having a shift register. What is the use of shift register? It is used for converting parallel data into serial data. So here you are using parallel to serial shift register in the case of transmission function, right? So in your transmit UART transmit function, you are using parallel to serial shift register. So when you are supplying a character A, ASCII value of A will be sent to this parallel to serial shift register, right? And based on the clock what you are giving in the parallel to serial shift register, one by one the bits will be sent out. First LSB will be sent, next the first bit will be sent, like that. So based on the clock which is given to the parallel to serial shift register, each character will be sent out serially through the TX pin of LPC2148, right? So whenever you are giving one clock to the parallel to serial shift register, one bit will go out through the TX line. When you are giving the second clock, second bit will go out through the TX line. So who is generating the serial clock? This serial clock is generated by a peripheral known as baud rate generator. That baud rate generator we have already seen while you are configuring the baud rate. So baud rate generator is a peripheral which is generating the clock required for shifting the data out in the parallel to serial shift register. And what will be the speed at which this baud rate generator is operating? That is what you have set in the previous step. I think in step 4 you are configuring it as 9600 baud rate. So when you are configuring the 9600 baud rate, you are in turn configuring the baud rate generator in order to generate a clock in that rate. So this baud rate generator will be generating the clock to the parallel to shift register in order to performing the parallel to serial conversion, right? So this parallel to serial shift register is a basic unit which is performing the conversion of a parallel data or 8-bit data to its serial form, right? So before sending a character parallel data to the shift register, you should check whether shift register is empty or not. Because if UART is performing the conversion, what will happen? Some data will be present in the shift register, and whenever it is given with a clock, one by one the bits will be going out. So if this process is going on, if the shifting of the shift register is going on, then you cannot write a new character. So if you want to write a new character before sending the character to the shift register, how will you send a character to shift register? That shift register is actually inaccessible to me. I cannot access that shift register directly. So that shift register is also known as a shadow register. I cannot access that shift register. So how will I access the shift register? How can I load this A to that shift register? By using a register known as this THR register. So if you are sending a character to THR, finally it is sent to the shift register, right? So before sending the data to a shift register or THR, what you should do? You need to check whether the shift register is empty, right? If shift register is empty, what does it mean? UART is ready to receive my second data or the next data, right? So in order to identify whether UART is ready to receive my character, you should check whether the shift register is empty or not. Which shift register? Parallel to serial shift register, which is used for transmitting the data. Right? You should check whether that shift register is empty or not. How will you do that? That is done in the previous step, fifth step. Right? You are checking whether UART0 is ready to send a character. That means you are checking whether UART is ready to receive my next character or not. How will I check whether it is ready or not? By checking whether the transmit shift register is empty. Right? If the transmitter shift register is empty, that means whatever data you have previously given to that register has already shifted out. So I can give the new data. So you are checking whether transmit shift register is empty in order to identify whether it is ready. So how will I do that? For that you are checking, you are using a register known as UART0 line status register. So all the status signals related to the UART is present in this register. In this fifth bit you are using for checking the status of transmit shift register. So you are having a bit known as transmit holding register empty bit. So if your UART shift register or transmit shift register is empty, what will happen? This bit will be set to 1. If your shift register is not empty, or if your transmit, because both the transmit holding register and transmit shift register, both you can use interchangeably, because transmit shift you cannot directly access transmit shift register. You can access it only through this transmit holding register, right? So the shift register is a shadow register. So what you should do, you are checking whether the transmit shift register is empty. For checking that, you can check whether transmit holding register is empty also. So if that is empty, that means UART is ready. So if that bit is 1, what does it mean? Your transmit holding register is empty, right? If the transmit holding register is containing some data, that means it is not empty, then it will be 0. So what you should do, you need to check whether U0 THR is empty or not. If U0 THR is empty, that means UART is ready to receive my next character. If U0 THR is empty or transmit shift register is empty, it means that I can give the new data so that it will be shifted out. Right. So what you should do, you need to check whether fifth bit is set or not. Right. So for that I told before, if you want to check a particular bit, what you should do, you need to split that bit. How will you split a bit? You need to AND with that bit alone as 1, all the other bits as zeros. Right. You need to AND with this bit alone as 1, all the other bits as zeros. So all the other bits will be matched with 0 except this bit. So this bit should be 1, all the other bits 0. So what is that value? 0, 0, 1, 0, 0, 0, 0. That means you need to AND with 0x to 0. So that is what is done. U0 LSR and 0x20. Right. U0 LSR and 0x20 means this bit alone will be kept as it is, all the other bits will be 0. Then what you will do? U0 LSR and 0x20, you are checking whether it is equal to, what you should check here? If it is 1, that means UART is ready to receive my new data. So in the next step, I can give the new data. If it is 0, what you should do? That means U0 THR is containing some data. What you should do? UART is not ready. So since you are using polling method, what you should do? You need to wait until it is 0. Right? So that is what is done here. While U0 LSR and 0x20, if that value is equal to 0, what does it mean? UART is not ready. So you need to wait here. So while a condition is true, what will happen? It will execute the statement. Since here we don't have any statements, you are putting semicolon here itself. So until U0 TSR, U0 LSR and 0x20, equal to 1, this statement will keep on continuing, right? When the condition given inside this while loop is true, it will keep on executing this statement itself, right? So, and at a particular point of time, U0 LSR and 20 will be equal to 1. When it will be 1? When UART is ready. So, when it is equal to 1, it will come out of this loop. It will break this loop, it will come out of this, right? So, if this value is equal to 0, if this value is equal to 0, that means U0 THR is 0 itself. That means UART is not ready. So, it will keep on executing the statement itself. Until this function is false, it will keep on executing this function. It will keep on executing this function. What does it mean? You are waiting until UART is ready. You are waiting there in the same statement. When the UART is ready, what will happen? U0 LSR and 0x20 will not be equal to 0. So when it is not equal to 0, that means UART is ready. So the execution will go to the next statement. So what will be the next statement? Give the character to U0THR, new character. So you should wait until UART is ready. That is done in this statement, right? So U0 LSR and 0x20 equal to 0. The same statement you can write like this also. Not of U0 LSR and 0x20. So here not is not a it is not taken as a complement operation. Here this exclamation, what does it mean? It is not a not operation. Inside while, this exclamation means whatever thing you are doing is equated to 0. So the same statement you can write like this also, right? So in this statement you are checking whether UART is ready. If UART is ready, then you will stop the execution of this while statement and you will go back to the next statement. If UART is not ready, this condition will be true. You will keep on executing this because it is a while loop. It will keep on executing this. Otherwise, it will go to the next statement.